All right. So since last week we don't have a class, and it's better for us to to kind of review what we discussed um, on Thursday, the week before last week. Where to share? All right. Yeah. So basically, we discussed a few aspects of the computational methods for additive manufacturing. And we start with this general process for additive manufacturing, how a 3D model is created and then sliced into layers, and then the tool path, the infill, all the planning are generated, also including the support material generation. And then all the digital files are passed to the manufacturing systems, and then a product will be manufactured. So that is the general process for the additive manufacturing. I mean, most of these process, more or less, they have similar steps. And also, we talk about some of these aspects, like this slicing, how to generate the infill, and how this will affect the efficiency and the mechanical property of the final parts. And so for the slicing part, we talk about the slicing algorithms. Basically, if we look at this, let me show the laser pointer. We have this model, which is represented by a mesh, right? So you guys all know what is mesh, right? Okay. So basically, a mesh model consists of set of triangular shapes, and basically the slicing algorithm is designed to generate the cross sections, right? A set of parallel plane with this triangular mesh model, right? And so here shows one contour shape of the layer, of the sliced layer. And basically, to generate the contour, you need to go through a plane triangle intersection. And here shows the different cases for this plane triangle intersection. And this is the plane equation, right? And you have three vertices of a triangle. And each vertex have three coordinates, right? And basically, this plane triangle intersection is calculating the intersection points. So there are different cases. So this one is the most, actually, this is the most common case for one layer. That is, there's no intersection, because only specific triangle will have intersection with one plane, right? So for all other triangles, there's no intersection. And you can compute the sign distance between each of the vertices to this plane, right? And if we just check the sign of this distance, if the sign for all this sign distance are same, that means there's no intersection, right? Or we have this one intersection case, or this two intersection case. And again, you need to check the sign. So if there's only one of this distance equals to 0, that means one intersection. That means one vertex is lying on this plane. Or if two of the three distance has different sign, that means there are two intersection points. But I don't remember who, but some students point out that could be some special case, like if this plane intersect at this triangle at one edge, that means you will have this distance, 2 of the distance will equal to 0, right? That could be a special case. And after you going through this, so you will immediately realize there are a lot of numerical computation. So for the numerical computation, there will be some accuracy problems because we are relying on the numerical computation to make judgment, to make those logic judgment, means there is intersection or not. This is depending on this distance. So you will immediately realize if the computation is not robust, that will cause problems. That will give you wrong layers. That will give you problems when actually fabricate this model. So that's the current status for this planar triangle intersection or the layer generation method. So you need to keep in mind, if the triangle shape is bad, means there's some very narrow triangle, or some triangle is very similar to a line, right? This vertex is too close to the opposite edge. You need to be careful. That could cause problems because this numerical computation highly rely on the shape of triangle. So probably you want to do some remeshing, means change those triangle in bad shape to some regular triangles. And it could be done by some mesh processing softwares. And I will introduce some of them later on. And that's the point for this one. And also the different ways of slicing, like uniform or adaptive slicing, right? We discussed this a little bit, but not much. We can discuss this a little bit today. So basically, as you can see, for this 3D model, actually we're using, if we use the 2-dimensional case to represent the 3-dimensional one, basically we're using those rectangle to approximate the original contour. So you will see there are some errors because the original shape will be this, but it turns out what you manufacture is this. What you accumulated onto the substrate is something like this. And this is the step error, right? And how to eliminate this? One way is just to increase the number of layers or decrease the thickness of the layers. So you have more layers, you will see this region will be smaller, right? And that gives you better shape approximation. But you have to pay the price that it will slow down your process. It definitely will slow down your process because you are printing more layers and your printing nozzle cannot move too fast. And that definitely decreases the efficiency. So people are developing some so-called adaptive slicing, means the layer thickness are not constant. So you could have really large layer thickness for some of the region of the 3D shape. But in contrast, for some high curvature region, you will increase the layer number. In other words, decrease the layer thickness. So by doing this, people are trying to find a balance between the efficiency versus the shape approximation. But I don't know, actually we discussed a little bit about this. Basically, this kind of adaptive slicing actually is not adopted by the mainstream manufacturer. I mean, the additive manufacturing manufacturer. So yeah.
Machines would have to, they would have to incorporate something to take advantage of that.
Exactly.
Different changing out the heads automatically or something to build real fine and real thick.
So what will be the parameter they will play with if they want to implement such system? So what's in your mind? Because if the layer thickness is different, so in my mind, the feed rate could be different. And I don't know whether the temperature, the nozzle temperature will be changed or not. And also, yeah, any other thoughts?
That was the issues that O&L was having
Yeah.
with the fan, was they were laying out so much material that it was contracting.
Yeah.
Again, you have.
Yeah. Yeah.
Can you adjust it?
Yeah.
Yeah. You might be able to do it with laser power with powder bed, if you
Yeah.
powder bed, but then.
Exactly. I think one big challenge here is again the heat management. Because if you have different, layer with different thickness, probably the rate of solidify will be of the material will be different. I cannot imagine what's gonna happen with this.
For the ones where you can use the epoxy, the resin system, resin systems would be much more adapted to that than something that you melted, because you don't have the same temperature. It just sets up.
Resin is refining layer, your resin, resin. You can't quench that far,
Yeah.
You can't do a thick.
Crystal
structure would be jacked up too. That depends what you do after.
Yeah, well, this kind of method actually they came up pretty early. I can see some paper even in 2007, 2009 something. So people in design area, they just based on this, they just published a bunch of papers. But it seems it's kind of a big gap between the practical solution versus some research. Oh, another thing, Michael. So in the subtractive manufacturing, do they have some like this adaptive subtracting? Means
Yeah, it's
But
speed and feed, and that's what it's all about.
so. Do you think
The bigger you can, chew through something, in the areas that you can, absolutely. Different tooling, different speed rates, speeds and feeds, and all of that.
Do you think it's practical, or people are actually using it or not?
Absolutely, that's how they make the money.
That is how
So
you do better than the next guy.
when I do Cub Scout work, they're about 5 by 5.
Yeah.
The fine layer thickness will take 47 minutes. If I do adaptive slicing, it's about 5 minutes. Subtractive.
You mean the machining?
The machine time goes way down.
It seems easier for the subtractive. To me, it's kind of you just do a rough cutting and then the fine tuning, right? The thickness definitely are different.
You still have to worry about heat management, but it's so much less of an issue than it is in additive.
Yeah.
So you can
I think
chew through stuff.
But it's a difference of if you're trying to cut a piece of wood, is it easier to use a saw or a Dremel tool? Right? Which one's more efficient? Saw it, unless you need fine detail, you're going to use the Dremel. If you're going to do additive, then I could see the benefit of having multiple heads, but heat is always going to kill you.
Yeah. I think the phase transition here in additive is the dominant factor to make the things complicated.
Yep.
All right.
One thing too is if you dump too much heat in that thin layer, right?
Yeah.
You also have to worry about melting the layer below.
Oh, okay.
If you get too hot,
Yeah.
and then it's going to start to sag, and you end up with these like droopy parts, right?
Yeah.
So it's got to be hot enough to create fusion between layers, but not so much heat that while it sits there, it's going to melt.
Yeah. Okay.
Or when everything cools, it cups up like a
Well, I would say people are actually seem to abandon this idea. They just keep on increasing the layer numbers and try to minimize the time for each layer, such that they could have a more efficient printing.
I think they may use some of this, like to a degree, not to the scale that you're showing here, but like maybe 0.4 millimeter versus 0.2. Right?
Yeah, that's
I
possible.
think some of the maker communities are.
Yeah, that's possible.
Perhaps.
Yeah, yeah. All right. Another kind of computation is the infill generation, right? You can see all the different patterns people are tested, like the honeycombs, the concentric, and zigzag. I would say the zigzag, it seems the most commonly used one. And
No, is this
Yeah.
just for the, I don't know the acronyms, is this just the deposition method or just the lithography method used in filling?
well,
FDM.
definitely
Mostly.
FDM.
Okay.
Yeah, it's for FDM.
Physically on a solid part, we've done some of the photography, if that's what you're trying to reduce weight.
Yeah, the purpose is kind of you mean for the powder base.
No, even with the stereolithography, if you're trying to make a model that they'd like to show the Eiffel
Yeah,
Tower, you want it to stand up on its own weight, but you don't want it to be solid, because otherwise.
So for the stereolithography, I showed you the carbon 3D, right? Basically, it continues through the bed and continues accumulate material over there. Actually, I attended the conference this last week, the NAMRC MSAC conference, which is the biggest one in the manufacturing area. So there are some papers. They are trying to solve the problems which carbon have. So all the demonstration kits they show is kind of lattice structure, thin frame structure. They're not dealing with those models with big cross sections because they still have problems when even they claim they put a dead zone and oxygen region are in between the newly created layer and versus the bottom tank. But the problem is this layer, this oxygen layer is uneven. So that will cause some shape distortion. And that will, turns out, damage the cross section generated for object with large profile. And some of the researchers, they are trying to kind of use a rotational degree freedom to make this oxygen layer evenly distributed or something like that. And the Invention Tech, the company, which is the main competitor versus 3D system, they claim they solve the problem. But in certain scale, again, with large scale, they still cannot solve it. So that is very interesting. That's, on one hand, they show those truss structure, those lattice structure, and people are fascinated. But actually, they are trying to hide the problem. They never show a printing with those large cross sections. So, well, it's kind of a very interesting problems they have. But come back to here, researchers try to optimize these infill patterns because what we have here is kind of some heuristic, right? Some empirical way to set up this. It's easier for people to just click a button and choose this. But definitely these are not optimal. So that's why people are thinking about to use the topology optimization for this infill generation. And it turns out they generate something like this. And you can see it's quite similar to what nature gave us, right? The bone structure here. So that is quite, I would say, amazing that actually nature is optimizing all the creatures. So I think I showed you the video, right? Yeah. Yeah. And then we talk about the topology optimization, right? And let's go to there and see whether you have questions. Because as I mentioned in the beginning of this class, for this onset session, I just want to slow down and discuss with you guys. And for the Zoom session on Thursday, I just speed up and try to cover the content as much as possible. So this session is kind of more like a discussion session, all right? So that is what I actually talked about last class. So basically, the structural optimization, or also as known as the topology optimization, actually they generate those optimized structure based on some finite element series. And also, other than the structural optimization, you could have also other optimization with like the fluid dynamics, not just the structural process. And you can see here this bracket object is also generated by topology optimization. And actually, this is not a direct result. They generate some shape similar to this, but definitely not manufacturable, or it does not look good. So based on what they generated, the designer redesigned this shape according to what they obtained from the optimization. And this one is kind of those so-called the Voronoi regions. But actually, this work is published on a very prestigious conference, but it has a very, I would say, deadly problem. So they generate the internal cavity in this model, but it turns out it requires support. And because this region is inside, so they cannot take out the support. So it turns out it looks you save the material, but you waste the support material. And I don't know whether it saves the material or not, but this is another example of this impractical solution from the opinion. They're computer scientists, and they just have some idea on how to generate the Voronoi diagram in the volumetric mesh, and they want to find a good application. And it happened at that time the additive manufacturing became popular, and they came up with this idea. But again, you cannot take out the support, so you cannot save the material. And actually, there's some extended work from other group try to generate those regions which can be self-supported, means no need support material. And it turns out make this kind of work. Right? So you can always see the disconnection between academia versus the real world. Right? And this one is kind of customized arm cast. And basically, the objective of the optimization is not only the structurality, but also it make the patient who wear it more comfortable. Because if you do not have any holes on it, that will be very hard when wearing it. And but how to distribute these patterns without sacrificing the kind of the protection, right? That is actually an optimization problem. And it turns out some algorithms is developed to figure out an optimal solution here.
So for the cast, they should incorporate customization into that so that you can pick a design that you want. Have it in there so that when you're out in the sun with your cast, you finally get your cast off, you have your favorite football team's hand to your skin. Avengers.
They've been doing the
Avengers.
There's a lot of
the casts.
Yeah, they paint something on the cast. Yeah. Well, that's a good idea. Yeah.
I'm sure I have a small like a lot of these examples.
Yeah.
They're just doing one thing. Right? Though lots of real engineering systems both amount of weight and it also uses heat.
Yeah.
Something like that. And that still seems to be an issue. I know they got to the point where you can handle multiple load cases. So, but this is really different load cases.
Yeah, exactly. I think for this kind of multi-objective optimization, you always have the pain to balance. Kind of if you achieve an extreme value means it is optimal for the structurality, or you can achieve another extreme for the heat emission or so on and so forth. But it's really difficult to know where is the weight to balance these two extremes. I don't see the the solution yet. Actually, that's a very tough problem to solve. People just don't touch it.
Yeah, it seems like now instead people are kind of, well, here's the historical solution, here's the solution.
Yeah.
I just made this one up in the middle.
Exactly.
So that's kind of where I've seen software that's MDM made, and it's addressing that exact problem.
Really?
Yeah, and they have a heat fin that's also got load as their example.
Yeah.
And what it is they'll have across the top,
Yeah.
there's different weights for different,
Yeah.
the load thing.
Yeah.
The weight load is 10%,
Yeah.
30% equal. It's kind of like a decision matrix. And then down the other side, they've got heat. And so they've got a square of all these different design options. You can see them on the screen and see how each one will perform. And so it's a decision by the engineer then to say which one.
Is it a parametric simulation or
It's so
So on the parametric, or, normally you said, hey, you can do this dimension, change this dimension this much, you can do that, but it's
No.
definitely got some constraints. where-
no, it's like voxel by voxel.
Okay.
So
What's the name of that one?
it's called. The guy's name is Ted Blacker.
Mhm.
And
Plato.
Plato, thank you.
Oh, okay.
It was it, we discussed it last
Yeah.
time.
Okay.
Yeah.
It's you can get government people can do it free. Maybe
Tons of
licensing.
I wrote it down in,
You need an Apple or a Linux.
Yeah, actually, what you described for the software Plato, what they did is kind of the current direction for this kind of software. That is, give the capability for the user to explore all the possibilities, but not just simply do the random combination. You have to give some train for the people to effectively and efficiently explore the design space. And that is, and also some more advanced algorithms coming in, like artificial intelligence, deep learning, so on and so forth. They're trying to help the user to exclude those not good design or impossible design, impractical design, something like that. Only remain those good designs or which is possible to be used in the application. So that is, I would say, a new direction for the CAD software or optimization software to go towards.
If I remember right, when Steen was doing his project, it was almost kind of like a verification tool saying, we're kind of approaching this design with the right philosophy, not necessarily having software do all the work for you, but having it kind of as a decision thing.
Yeah, it's almost like it's a supplement to the engineer's intuition.
Yeah,
Or
yeah. Exactly,
something like that,
exactly.
right? It gives them that first step to say, this is kind of where I want to go with this.
And LS Stein and some of the others have the capability to now take that topology and then
you
do the
can export it.
You can export it from that, and there, the Tesla thing can't stand up on this program. But it looks great.
Ryan, you caught it. You could just run a test employee.
I would love to have that.
Yeah, well, the thing is, because I'm in the design area, and a lot of my work is try to develop some new design systems, which will kind of extend the capability of designer, and also it's easy to use. So actually, I'm kind of think, because right now the CAD software or other optimization simulation software is kind of you are using a screwdriver or hammer. Basically, the only difference is between using a physical tool and that tool, the CAD tool is kind of you are operating a computer. But all the rest are similar. You need to take care of everything. There must be something in your mind. Like you have to have some idea about the optimal design. And you have to specify all the parameters, all the shape. And then it turns out the CAD software generates something for you. But that's still lack of automation. It's still a lot of low-level work is done by human, not the computer. So, well, in my mind, the future of this kind of software should, like, they will do the low-level work. They will buy some like maybe artificial intelligence algorithm or something else, and they learn the designer's knowledge, and it turns out the designer will only handle the high level, and they make decision based on what is suggested by the software. It's something like that. I don't know whether it's, but of course it's a long way to go to achieve what I described. But it's kind of I'm believing this should be a possible direction, yeah, for the development. So actually, I'm paying some effort on this, but still very preliminary. All right, let's move on. So other structural optimization work will be used for those structural material in those small scales. Like, as you can see, these hierarchical unicell structures, right? And it gives the material some new properties like negative Poisson ratio or some properties, not only the mechanical property, but also some optical or electronical properties because of this kind of new structural optimization. And as you can see, this one, they print this, it seems to be the, what's the name of that? Graphene. This, yeah, graphene. Yeah, they use some type of graphene and print these structures. You can see how light it is, right? And this is another trend that people adopt this structural optimization to the small scale. But to me, I don't get it. Is the point I don't get it is, seems this type of work and this type of work, they are disconnected. To me, the seems share the same fundamental. For the optimization, I don't know why. It seems, I mean, it should be unified to me. I mean, in terms of the method, but I didn't see much people work in both areas. And I don't know what could be the reason for this kind of material modeling with structural optimization versus those macro level structural optimization.
This is kind of like a field, right?
Yeah.
You know, you have the part and you're designing the geometry,
Yeah.
and this is usually looked at as, what am I going to make? You know,
Yeah.
my raster path. What is my field? I have seen some where you've probably seen too, where they adapt the mesh. You know, the structure changes as you go across the part.
Yeah.
Well, if you had, sorry.
Yeah, go ahead.
I mean, if you have like a dog ear, right, that you're going to put a hinge bolt or an hinge through, then you'd analyze it as one solid piece of metal, right? So you can put a honeycomb in it, and that one solid piece of metal is now stronger, or the honeycomb is stronger than one solid piece of metal, until you put that stress concentrator of that one hole. So would this be an application where you would increase the fill around the hole to divert that stress, so it's not going to propagate a crack? Is that what that's for?
Usually you don't put this stuff at your interface. Like, you would make that area solid. But
Yeah. I mean,
I wouldn't design something so that I have that material and it's like I drill a hole through it.
exactly.
It's just two different things to scale, right? I mean, for this one, you need to really change the material properties instead of just current elements.
Yeah, I think that could be one reason, because people who are working this kind of work, they are basically material scientists. And the people who are working in this one, they are mechanical engineers. They don't talk to each other.
This seems like an area though where more it's just people are, as opposed to having a problem and trying to solve it. This is more of one of those areas that they just moved out into, that this capability can do this. Not real sure about the perfect application for it, but this is cool. This looks awesome when you pick it up and it has this tiny little, honeycomb structure. But
So it looks to me as with the bone,
the mechanical engineers were trying to model exactly what was there in nature. This looks to me like the material scientists are trying to replicate the atomic structure that's there in nature.
Kind of, yeah, I
Bring
agree.
it up.
Well, yeah. But anyway, actually, I don't know. I'm talking to some material scientists and trying to take a foot into this region and see what's going on there. And I don't know. Maybe I can do something.
I mean, just in general, just me knowing very little about what's going on, but took a tour of NDF 5, 6 years ago, and there were these kind of parts everywhere.
Mm-hmm.
Took a tour of NDF last week.
Yeah.
Saw maybe one piece in a cabinet over in the corner that looked like this. You know, I mean,
Yeah.
I think that was, to me,
Mhm.
from the outside, looked like an area where people, this technology can do this, and we're going to play with it, but the application of using it
Yeah.
is not
there.
there in a lot of
Mhm.
things.
And there's manufacturing issues with these on the
Mhm.
AM systems, even though it looked great, like the horizontal members on a metal
Yeah.
machine tend to sag or
Mhm.
droop, and sometimes they're not even connected. You know, so you've got manufacturability issues with this.
Mhm.
So if I was, and they're engaging more designers there too,
Yeah.
now they're engaging, you know, fabricators, trying to find more applications that's useful.
Yeah.
So it's going from those, you know, Brian Day Hoff, those guys, they're all material scientists. That do metal stuff, so that's why you saw. Got me interested.
Yeah.
The first thing we designed had planets in it.
It's cool.
Okay. Anyway, yeah, let's move on. So basically, here gives you some idea of topologization, and it's a mathematical approach to optimize the material layout within a given design domain. And basically, you have a bunch of constraints and boundary conditions applied, and the algorithm will automatically generate a material layout. And as I mentioned, let's just skip this because we mentioned a lot. And that why topology optimization becomes so popular recently, because finally there are some manufacturing methods can fabricate what it optimized. So that's why people are calling that it's kind of a perfect marriage between topology optimization and additive manufacturing. And for the toy problems, okay, let's simply go through it. So basically, the toy problem actually gives you the concept of topology optimization. See, we have 20 by 10 grids. So in total, 200 grids. But we only have 60 Legos, and each Lego will be placed onto one of these grids. So what will be the optimal layout you put the Lego such that it has the stiffest structure? So if you talk about the overall possibility, that will be a pretty large number, and which is impossible to explore one by one. So, and you could have different patterns, like the simplest one like this, right? Just make a block, or something like this, or you could have something like this. Just remember, where's my, okay. So basically, this is fixed, and the load is applied from this side and on this point. All right. And it seems this one is pretty good candidate to be the most optimal one. Which one? This one?
Yeah, you don't have any overlap.
I know. Lego's gonna fall.
And
It's a room full of dads here. We know Lego.
okay. Basically, this is the one if we apply the load and do a FE analysis and display the displacement map. And you can see design A and B, they are undergoing a large deformation, right? But for the C, almost no deformation. And apparently, the design C is pretty good. But the problem is how to find out this one from the original 20 by 10 design domain. So that is essentially the topology optimization trying to solve. And So that's the concept for the topology optimization. And this is a typical formulation for it. And you have this objective function, which is so-called compliance energy. And the U will be the elements string. And the K is the element stiffness matrix. And you put them together and add all this energy of the elements, you will have an overall compliance energy. It measures how stiff or how soft your structure is. Right? That's the objective function. And then you have several constraints. So the first one is the volume constraints. Means how many volume you want to keep, right? Because if the original design domain, you can consider about it as the 100% of the volume. So you can choose maybe 20% of the material remaining, or 30% or 50, or something like that. So it will be represented using this constraint. And this one is the so-called the static equation. That is, with current status, what will be the finite element problems you're solving? And but I should introduce this at the very beginning. So basically, this is the actually the variable we want to solve. So, and this rho actually means the density of one element. So 0 means there's no material put on this grid. 1 means you just put the material there. So this rho will vary from 0 to 1, and it turns out it will give you a distribution of the material. Of course, you cannot have the binary number 0, 1 by going through this optimization, because it's numerical optimization, it's continuous domain. It's kind of, you only have some very small number of the rho, and at which you could set up a cutoff value. That is, if the rho is less than, let's see, 0.001 or 0.0001, something like that. If the value is less than that, you just consider it as 0, something like that. So that is the whole formulation for the topology optimization. And here gives you the simplest stiffness matrix versus this strain value. So if we're talking about some spring mass systems, that will be your stiffness matrix. And yeah, go ahead.
Can I ask about the
Yeah.
density? So is the density saying that each individual
Yeah.
square is going to have a different density?
Yeah.
So like the previous picture where you showed it was more of a shaded version of that.
Yeah. All the black regions will be the one with very large,
So like almost one.
almost one, kind
And
of.
then there's some that look like shaded ones. Are those like somewhere
In between, yeah. It depends on how your cutting off value. If you set it big, maybe this shaded one will become a void. If you set small, these ones will be remaining. Something like that. All right. But of course, you will have more complex setup if you are talking about some complex systems. All right. Yeah.
Not really the balance, like stress out. So, so there are other formulations that are trying to even out the stress throughout the part.
Yeah, from this setup, when you solve your finite element analysis, you could recover because even here you're not solving the strain directly. You will have the displacement instead of strain, and using the displacement, you can recover everything. The strain, stress. Well, yeah.
It's like it's optimized.
Yeah.
Isn't it if you have the same, if you have the optimized stiffness for the amount of volume you have, do you not have uniform stress then?
All these software packages work off a certain boundary conditions.
Yeah.
So you say, I want my mass to be half the mass, but I want to maximize stiffness, or I want to have the least mass and maximize, so you always have to play the trading game.
Actually, this objective function and all the constraints could be different for different problems. If you are talking about some kind of thermodynamic problems or heat transfer problems, you will have totally governing equation, which means this one will be different, and this one will be also different. So you will have some kind of other values, but similar, but all the routine, all the formulation are quite similar to each other. But according to different governing equation, you will have totally different physical meaning there. But the routine is quite different, quite similar. And basically, you are doing some iterative solving. So first of all, you just set up your density to be 1. So that means at every grid you have material, and then you just keep on solving this and update, the row, and solving this, update row, and then you will check whether the change of row become too small, or the energy, this objective function, the change of this objective function become too small, or some other conditions. You just check it. If it is satisfied, this operation will be considered as converged. Then you just stop the iteration, or otherwise it will keep on running this. So it turns out we'll give you a structure like this. Of course, there will be some other tricks to make sure the generated region will be some link region. They put just some filters, so-called filters, to kind of propagate your strain or stress, such that you will generate the connected regions. Otherwise, you could generate some chessboard regions. Means all the holes distributed on the whole domain, and well, it's not a valid design. Of course, there will be this kind of tricks to make your solution as practical. Yeah.
It looks like they also had some algorithms that would go through, you could pick like a minimum ligament like thickness, and it would go through and verify that things didn't get too thin. So
Exactly. Yeah.
It seemed like it slowed it down quite a bit depending on the size.
Exactly. Yeah, that's true. Because the computation will rely on the size you selected. And if you select too large size, that means you are essentially solving a global problem instead of a local problem. So always localize your optimization will definitely speed up your computation. But that's a trade-off. Sometimes you have to make it global. But, well, that could really slow down your computation. Yeah. All right. So for this, I just kind of skip it. Actually, I want to show you one of the paper I'm working on and some results. I'm not sure whether I have. Let me find it. Because recently I'm working in this area, so I'm kind of have some new thoughts on that. Paper figures. Just show you some result maybe.
I don't remember what particular software we were looking at.
Yeah.
With Steam, but we had to force some of the solutions out. Technically, it was giving us the right answer, but not what we were looking for as design engineers. So it was giving us the optimal answer, but it wasn't what we wanted.
Yeah. And also another difficulty is how to set up the load on the boundary conditions. So what you set up actually is just a one, it's kind of a approximation of the real case. So you need to think about whether your approximation is reasonable or not, whether it reflects the real world situation or not. So basically what I developed actually is a topologization for this kind of customized, did I share this yet? Let me share it. Share. So this kind of customized arm cast or those compression braces. So what I did here is instead of using the 3D elements, because it's 3D shape, but instead of using 3D elements, I use 2D elements. Because this kind of problems, the thickness of the object is pretty small compared to other dimensions. So I use the same plate theory as the governing equation for the finite element analysis. For the same plate theory, you can consider about the design domain as 2D elements instead of 3D one. So that's how I kind of have a great speed up. So I use the Tosca, actually Tosca, to compare. This is the one generated by Tosca. It takes us 2.5 hours to get this because it uses the standard 3D elements. And I don't add as many loads as what I did here. For this one, I added a lot of load. But for this one, to make a solution, because if I added too much, it cannot give me a solution. It will take infinity time to process. I only have to add 5 or something. And still it takes 2.5 hours. But for this one, for this arm cast one, it takes 2 minutes, 2.5 minutes. So you can, yeah.
2.5 hours on how many cores? Like, parallel?
Yes, parallel. I pick up. I select all the optimized solution, and I use the same machine to do the testing for my algorithms and the Tosca. So to be.
Relative, relative.
It isn't Summit over here.
Yeah. It kind of.
To do this for the shroud.
Yeah. Yeah, as you can see, here is the result generated, and also I print it out and wear it. That is because the body, the human body here is my body. And so I generate result and print it and wear it. And you can see how it looks like. Well,
you have to break your own arm to.
No. Okay. And anyway, I also do a leg cast and also this kind of brace to straighten the spine. Yeah, something like this. So yeah, that's one work I'm working on. Yeah. So it's not general. What I developed definitely is not general. But for specific domain, I could have much more optimized solution in terms of efficiency and also the result. The effectiveness. Well, that's one attempt I'm working on to make our computational tool useful for the designers. All right. Okay. Let's go back to our slides. Oh, wow. We can have a 5 minutes break because it's almost 15 minutes.
So, I told about a company in Nashville that does that. People pay a lot of money, but you say, I want to look like this video game character. You go down there. They scan the body and then they custom fit the costume. Yeah. So if you want to look like Master Chief, they'll print it. I ran into Boba Fett.
Yeah.
Like, that's a really good fit. He's like, oh yeah, custom over here.
Yeah. I mean, if there's a market for it, then
There is a market for it.
Actually, there is market. So do you know what is the purpose for me to scanning my body? Actually, it's not for this problem. I did it 10 years ago. So back to Of course, the body shape is much better than right now. But the thing is, at that time, I was working on a project developing a customized wetsuit. So for those kind of pro level wetsuits, I mean those athletes, like they're working on those windsurfing or diving, they really have the needs to have a really tight wetsuit. And that's why we need to really scan the body and develop a automatic design system for it. And it turns out we licensed to a French company who designed a high-end wetsuit, and they are still using it. But again, the market size is relatively small. Not much people will buy it, although the need is there. That's why I didn't work on this.
That's why I just say, hey, I'm gonna make body armor for military.
We did a printed structure like that with hollow tubes in it. What they wanted to do was force coolant water under there, cool it down, and then do heat management.
Yeah, one of the senior design projects when I was in school was for Air Force Research Lab, and they did a coolant thing where they pulled like a vacuum around your arm and circulated coolant.
Okay. You want a design system?
I worked on that stupid one where the Navy said, "Can you make jet fuel out of corn?" They said, "Yes, we can." And then Congress turned around and said, "You need to have alternative military fuel."
Yeah, that's
Energy competing with food. So, yeah.
okay. That's good.
Yeah, my 3-year-old broke his arm right before we went on travel to Virginia Beach. So
Yeah.
we had a traditional cast on, trying to keep a 3-year-old with a dry cast at the beach.
Yeah. To me, it's really challenging to kind of figure out a research which could solve certain level of the practical problems.
Yeah.
I don't like the type of research just for people.
Yeah.
It solves nothing.
Yeah.
It's junk research.
Yeah, there's always a balance between solving real world problems, but at the same time you want to do something new, novel, innovative.
Some of the stuff that we actually use a lot. So they print size. And they customize. If you have like a compound fracture, right now they're what they're doing is they're scanning the bones and they design to put a clamshell screw together assembly. They put it over your bone, so it's customized to the shape of your bone. They put a texture on the inside that promotes faster bone growth. Like doctors, all the PhD doctors are coming up with these textures that they claim makes bone growth.
Yeah.
And then it's made out of an easy amount of balls.
It's called scaffold.
Scaffold.
Scaffold structures
Oh,
to help the growth of the bone and tissues.
Yeah. Yeah, there's a lot of biomedical stuff with materials and bones.
Yeah.
Because that's where the demo is, right?
Yeah.
I mean, medical.
But-
Yeah.
I think that doesn't do that. It's our damn insurance. That's our premium.
Yeah.
They're not paying for it.
I didn't say whose money. I just,
But the thing is, again, the 3D scanning is still problems. You have to do a lot of massage to the model
yes.
you're offering.
Yes.
Well, that's really the barrier to many of the applications.
Yeah, because we were getting all those, like the structures you were getting with Fresca, and like you can't use that for anything. You still have to take that and do all sorts of post-processing to the model, just do anything.
It turns out you need to train a CAD engineer to do all the dirty work in the back.
It was a lot of work.
A lot of work. I know because I did a lot of scanning, and the model I showed in the size of my own body. Basically, 2 CAD software engineers, they did for 2 days to clean up all the holes, all the non-manifold things, and clean up all the mess on the head. Because basically my hair is black, and when do the 3D scanning, there will be holes. I have to wear a cap, a swimming cap, a white cap, to make this as beautiful as possible. But still, it requires a lot.
Yeah, I mean, there are some software packages that are very good at,
Yeah.
all they do is mesh manipulation type stuff.
Yeah. Yeah. But still, a lot of manual work. You can use that
absolutely.
as tool, but
Yeah.
still.
Yeah, we took some stuff out of like a 3D point cloud.
Yeah.
And then tried to bring that into something that you could do something with. And, you know, after days, we're like, you know what, it's just easier if I reproduce it in CAD.
Yeah.
Like,
It's pretty difficult.
Yeah, it's good.
well, but see, that's my big problem with,
Yeah.
everybody loves additive manufacturing and 3D printing, and, you know, oh, it's great, right? Well, so you look at where Creo went to, Creo had these organic shapes that you could start with.
Yeah.
And they're like, oh, here's how you make a shampoo bottle, right? And so they took a sphere.
Oh, and you like
And then
drag
you
it.
just draw it up, and you
Yeah.
drag it up, and then, all right, I'm gonna put a hole through here. And it's very organic, and it's
Yeah.
very, but as an engineer, I do numbers, right? And so, hey, this needs to be, you know, it needs to be 6 millimeters wide
Yeah.
so that I can fit this through. And as nice as this little
Yeah.
shampoo bottle was, it's not very functional because it had to make screw threads from the top
Yeah.
and so on and so forth. And it just, there's this beautiful meshing of artist and engineer
Yeah.
somewhere in additive manufacturing.
And let's say you're gonna have those injection molded. Well, you have to come with mold, and then you have to do GDT of your organic shape. Good luck trying to do that.
Right.
Yeah, that's really disconnected between the manufacturing versus the freeform surface
Yeah.
modeling.
Yeah.
You can see the gap clearly here.
We had so I saw someone's drawing package that they sent out to get made. And asked the guy, but are they new? Have they done this for you before? Like, oh yeah, they've done it a couple times. So they made this thing out of wood, all right? And it's like, yeah, it's a 2x4, and it's 1.50 by 3.50. I'm like, okay, so those are custom 2x4s because that tolerance, you're gonna have to cut every single one of those. Oh, well, no, that's not what, like, and so we started going through it. It's like, there's a big difference between design for manufacturability and, hey, I drew some stuff in solid.
Yeah.
No, you're John. I mean, all this is the union guy just says print it, man.
Well, I mean, one of the most beautiful things I ever got to see was on-machine programming of a lathe with live tool, right?
Yeah.
Because you can sit there and draw what I can draw in Pro Week, and then he could hit the go button, and it would make it.
Oh, like conversational programming to the controllers and all.
Yeah. So, I mean, he could model the part on the machine, and then the machine would say, all right, I'm using this tool.
All right. So after we have all the tool paths, everything there, we need to generate the tool paths, like eventually pass to the machine systems using the G code. I think this probably you have a lot of knowledge on it. I just fast kind of skip it. So another problem you have to deal with using most of the additive manufacturing process is you need to generate the support materials to support those geometric features which required, like overhanging, floating, sailing, unstable, or base support structures. Right? And so usually how to define a geometric feature which requires a support structure, we use this this angle here. So if this angle become larger and larger, usually larger than 45 degrees, that means you probably need something to be there, support your features. And another thing is the building's direction, orientation, exactly. So you can see for the same one, or if you just randomly put it into the 3D printer in this direction, oh, okay, you have to print so many support material. But why not just do it like this, right? It's self-supported. So I think usually for the novice users, and they just do something like
You
this.
send two people off, and when this guy walks back and the kids, he looks down
You got your A, your B.
yeah, he goes, crap.
Yeah. Yes. So you can see it's so simple, right? You just rotate it in 90 degrees, and then you have no problem. But the thing is, many people don't have this concept in their mind ready, right? So that's one thing. Another thing is see how the angle this angle will affect your printed result, and you can see how bad it became when you just make this angle bigger and bigger, or basically this measures a different angle, but you can see is how the feature is damaged because lacking of the support material, right? And other work focused on optimize the support structure, which will reduce the usage of the printing material. And this is the conventional support material for FDA. So it's kind of, you just, basically the conventional method is kind of, you just make sure it won't fall down, right? The feature can be printed successfully, and actually it requires more than needed, the support material. And this kind of a tree-like, where it is, tree-like support material, actually you can see how much it was reduced compared to the conventional ones. And actually this figure from this paper, but there are also some commercial software with, what's going on here? I don't know why, but it seems stuck here. My slide's stuck. So there are some software like Autodesk Mesh Mixture. They already embed this kind of smart material support material generation approach in their software package. Like this is what they generated, and this is what Cura generated. You can see how big the differences is. And yeah, I usually use this software to generate the support and save it as the same as one file, and then just put it into Cura and select no support, because this itself will self-support itself, right? So then I do the slicing, because it uses the same material. I mean, it depends on the support material used. If you use the same material, so you can choose no support material. But if you use different material, you can import this model by two model. One, this dragon model, another, all the support material, and you choose different material for the two model, such that you could still use Cura to generate the slice the layers. And also, yeah, go ahead.
Have you ever tried to check the mesh mixer to say import it with the supports and then say make supports in Cura and see if it makes any additional supports, or does it agree with mesh mixer? You see where I'm going? So if you, for your dragon, you generate the supports like shown on the left, and you take that summary, the support plus the part, put it into Cura, see if it pretend like it's the part you want to make, and then see if it will generate.
Actually, I didn't try that, but it's possible, because
See if it creates lines underneath the support material. If it says,
You're done, Domino's.
Because I believe topologically this part, they're not connected. Although for the geometrically they are located at the same position, but topologically, they are two different models. So I don't know whether Cura will be aware of this, or they just still generate something like this. I can have a trial. No, I didn't try this model, but I tried others, and I didn't try what you suggested.
How do those?
Yeah.
The
Yeah, you mean these ones? Yeah.
long slender member supports that you have. Do they print okay? Have you
Yeah.
tried those?
Yeah, it works pretty good. Yeah, it works pretty good. Yeah. That is what, actually I did some comparison with what Max Mixture generated. And I use this instead of this because I just don't want to waste my time, because yeah, you will see that work later on. Yeah. This is a kind of a additive manufacturing worksheet, which is based on a paper by my former colleagues at Purdue University. So what is this? So basically they noticed that try to successfully print something using additive manufacturing actually is quite challenging for novice users, because they have very limited knowledge on design and engineering. So instead of just to push them into this domain, so my former colleagues, they developed this worksheet. Basically, you just check what you CADed, what's a model you designed in your CAD or other software, and see. And based on the model, you just check these options, and turns out that gives you a total score there. And based on the score, you can tell how likely what you designed could be successfully manufactured using additive manufacturing. So something like that, it's kind of based on some heuristic or experience from the engineer, and could be a guidance for some novice users. But actually, this is quite limited, I would say. It requires still the manual input from the users, and they might make mistakes if they are not familiar with engineering or design. And also, these features are quite limited, right? A lot of cases just not covered. So actually, I was thinking about to come up with some computational tool with all this knowledge integrated there for some better experience for the novice users. But it's still ongoing. But the point is, to successfully printing something for novice users is still quite difficult. That's the point. So there are other computational methods they are developed for better appearance for additive manufacturing, and like this kind of color mixing approaches. So basically, researchers are trying to make more good-looking color or some continuous transition between one color to another by optimize their printing algorithms. And this one's called layer shifting to alternatively distribute a black and white nozzle, material, such that you could have some shaded effect. And another effort from the software algorithm side. So they are not trying to develop new machine systems. Instead, they are trying to optimize the distribution of these layers in different colors. So some result will be like this. Well, I don't know. Maybe it can be solved entirely by just using some multi-nozzle printing system. So, but still nice efforts in software side. And some polyjetting 3D printer, they are really good at printing those multi-material and multi-color printing. But modeling could be a challenging problem, because they usually use the so-called voxel representation, like the one shown here, right? That means they use the small cubes to represent the whole volumetric model. And the computation could be going to some crazy level if you have very good detail, very fine detail like these ones. So it requires efficient computation. And this is the so-called the error diffusion with the translucent material. Basically, they are using a half-toning, a signal defined on a surface such that they use less computational power and memory to generate an even better, appearance like this.
So yeah, what it is, it's something on, it's your insurance.
Each color is 2 different tints.
But the face is printed.
Yeah, the whole face is printed using the polyjetting, and they use their modeling approach. I will show you the video. Let's take a look. Yeah, this one is pretty good compared to the previous shaded one.
Is this a photograph? Is this a photograph just supporting a concept, or is that actually a face?
That's the physical printed part. Yeah, not photo. Otherwise, people are not convinced. Oh no. What's that? Yeah, let's.
Yeah, because
It's a nice model from the document.
I thought it was pretty impressive.
Shell.
The different shade on the.
You know what?
the logo.
Yeah. One possible application coming to my mind is those plastic surgeries. You can just 3D print what you want to become, right? Okay, right? But
17 models of Barbie.
yeah. Yeah, that's something wrong with my slides, and yeah, let's. Oh, not this one. Shoot. What? Oh, I'll just close this one.
The Iron Man 2, Iron Man 1, the printed is. Yeah, something like that. You know. Just do whatever.
3D printed.
All right, let's take a look.
Accurate color reproduction is important for many 3D printing applications, such as design prototypes,
Oh,
or
not
3D
showing
color
there?
copies or portraits. Currently,
How should I share this? Can I? Oh, okay. Good.
Hey, Kevin, if you could do that, it's a nice
new 3D printing technologies allow for full color, powder binder, and layer laminate systems. Compared with these technologies, multi-jet printers reproduce surface geometry more faithfully, and more importantly, they allow arbitrary configurations of materials with different optical properties, such as transparency or color. This gives multi-jet printing tremendous potential for graphical 3D printing in terms of reproducing complex visual effects and optical properties, but it currently cannot print in full color, limiting its applicability. Color reproduction in multi-jet printing poses substantial technical challenges due to the high resolution and due to the high translucency of color printing materials. In this paper, we provide a critical building block for graphical 3D printing, accurate color reproduction with multi-jet
Just see the value.
From a technical standpoint, our contribution is an error diffusion approach which operates at printer resolution within a streaming architecture. Our approach consists of 2 main steps. We construct multiple layers within the object and assign printer tonal values according to the input texture. Each layer is then half-toned independently using an error diffusion approach. We propose a traversal algorithm for voxel representations of surfaces, which allows us to map a 2D error diffusion filter onto the surface in a consistently oriented way, letting us leverage 4 decades of error diffusion research from 2D printing. For technical details, please refer to the paper.
It's kind
Our
of
approach scales from small prints containing 100 million voxels to large prints with tens of billions of voxels, delivering the first set of slices to the printer in a matter of seconds. Now, let's look at some more results. Our prints show unprecedented detail and realism for color 3D printing.
yeah.
Thank you for your attention.
All right. Yeah. Yeah. So.
So much for waxing.
That's, where's my? I think I will go back to the slides. All right.
Who says they haven't already?
So, yeah, so for the details, we can check the paper, but the concept is kind of, because for the image diffusion, we have tons of paper about it. So basically, that will help you to generate more realistic image. But for the 3D version of the image, which is the voxel representation, they kind of extend the work of the 2D version to the 3D one, such that you will have more realistic result without sacrificing the, without use too much computational power or memories, because that will eventually cause problem to your computation, like to your computer. So, and it will take infinity time to process. So that is their contribution. They develop this smart algorithm to do this. And let's move on for other work. So another, this is the 3D, the topology optimization we have covered. And another interesting kind of interesting work is the new effort for the manufacture, the functionality. So the functionality here we are talking about is not the material functionality. It's not the functional material. It's more like the component functionality. So for example, if you want to have a customized ergonomic aware mouse, how are you going to make it using current additive manufacturing systems? Yeah, basically this is my hand. Yeah, I use a Play-Doh, the physical Play-Doh, and shape the mouse, and then use a 3D scanner to scan it. And then I will design it using design software or just simply using CAD. But the thing is, this is just the shells, the appearance for the mouse. It has no functionality. It's not like something functional like this. So there's a huge gap between the object with only appearance versus the object with a full component functionality. So how to achieve this, right? So that is the research problems. Actually, I want to kind of address in this work. And also there are other difficulties in current additive manufacturing because they're only single process for generating the geometry, like this one, right? You just accumulate the material onto each layer, right? And no other process for the functional component embedding. That means you just generate the appearance of the object and then assemble them together with the functional component together, right? So that's the typical way people utilizing additive manufacturing. Actually, that is what I did for what my student did for their project of the design for manufacturability. So basically, I was asking them to design a functional toy and using additive manufacturing and other manufacturing methods. And what they did is they design the appearance of the toy. They 3D print it, and they purchase all the components and assemble them together. Eventually they make it work. But that requires the human involvement a lot, actually. And you need to come up with the idea of assemblies, how you're gonna assemble them together and design them using some certain CAD software. And also it requires manual assembly, a manual assembly here. So for the novice users, for the average users who are not the engineer or engineering students, they have no such capability to design and assemble the functional objects. Also, the unidirectional printing scheme limits the toolpath planning. So what does it mean? So for the support material, I mean, if we talk about the support material, because we only have one printing direction. So for a sphere, even as simple as a sphere, you need to print support for this region, which points downwards to the printing direction. And also use just one printing direction. There's no way to embed other components into the printing process. So as you can see, these regions will be, the region cannot be accessed due to the width of the nozzle, right? And also the bottom part of this enclosure is not accessible. So that prevents the automatic embedding of functional components. So that suggests we need more degree freedoms. We need to introduce more process into current uni process and unidirectional additive manufacturing process. And this is what I come up with. Basically, it's called Ribbon Maker. So you can see that the printed 3D the mouse. So we generate a cuboid inside the 3D mouse, and then we pre-assemble everything into this cuboid, which is much easier. And then we just rotate and print all the geometry onto this cuboid. As long as we finish the printing, this is a totally functioning mouse. We could directly use it. So what we achieved the so-called direct out of 3D printer functionality. Okay, something like this. And so the workflow, like we just generate a cuboid and embed all the functional components inside this cuboid base, and then put it onto the 3D printer. And then we have 2 rounds of revolving and printing, and all the appearance will be printed onto this cuboid. So this is the second round of printing. And it turns out, because we print 2 handles such that this object could be gripped during the second round of printing. But after the whole printing is done, we just remove the 2 handles, and we have the original geometry printed onto this enclosure. And so the most essential part here is how to generate this cuboid for the printing base and as the housing of functional components. Yep.
So the multi-axis print system already exists?
I think when we built this is the first attempt. But because this paper is published in 2015, there's not much work done there. Although there's some robot-based printer, which gives you the multi degree freedoms. But the thing is, they didn't achieve the complexity of what we achieved. Also, our focus in this work is the algorithms. As I will introduce it right away. Yeah. So yeah, go ahead.
The printer has no way to tell if the functional component is intact. So how attached to the box was the final grip on the mouse? Pop off after a year?
Oh yeah, you mean how long it can last, right? not long. Not long. You are totally right. It's just a proof of concept. I'm sorry. It's not achieved. It hasn't achieved the level to be practical or can produce the actual product. But the concept is what the multi-degree freedoms will bring to additive manufacturing, and what will the different printing direction will benefit the additive manufacturing, and that is what I'm going to talk about. So basically, I developed an algorithm called the cubitization algorithms. So the cubitization is a made-up word by us. So basically, it means it generates a cuboid inside a 3D model. So what's the target for this cuboid? So we would like to have as large volume as possible, such that it takes as large volume as possible of the 3D model. That means you could print less material because the volume is taken by this cuboid base. Right? That's one objective. Another one is we would like to have as little overhanging features as possible. Why we have this? Because in the video, we could have different printing direction without just one direction, instead of just one direction, such that we could design some algorithms when generating this cuboid. All the 3D model could be divided into pieces to attach the 3D model. And for each of a piece, you could have a specific printing direction such that there will be as little overhanging feature as possible. And actually, we'll achieve totally support-free for all the 7 tested models, and I will show you. Yeah. So, and eventually we come up with this objective function, and considering the difficulty and the cost of removing overhanging features, we set it as the hard constraint. That means it has to be certified with higher priority. And this volume objective set it as the objective function. But directly solving this is kind of impossible. Why? Because to evaluate this function, especially this overhanging function, is so difficult. And it turns out we come up with a 2-step optimization and how it works. So for a 3D object like this, you can see it's pretty simple. But the thing is, it has 2 tips, 6 tips in each of the direction. So it turns out there's no way to print it without any support. No matter how you orient it, because it's kind of a symmetric shape. So no matter how you orient this model, you have to print some support material somehow. So, what we did is we generate the cuboid. Here shows the algorithms. It's kind of a real-time rendering of how the algorithm search for the optimal cuboid. And you can see we generate M samples of the cuboid orientations. What is the cuboid orientations? Because for the cuboid, it has 3 axes. And each of the axes align one of the principal dimension, right? And we call it the orientation of the cuboid. Basically, there are 3 vectors. We do a sampling of these vectors for each of these samples. We just generate 1 cuboid like this. So as you can see, for each of the orientation, we will have 1 cuboid, and each of the cuboid will divide the whole shape into different segmentation for the printing, like something like this. And for each of the segment, we just evaluate the printing sequence and the overhanging features. Why the printing sequence matter? As you can see, so this is the cuboid, and here all the colorful regions are the divided regions. And there are some black regions, which you could have different sequence to print. For example, if this region is printed with the yellow one, you will have something like this, some region like this, which requires support material. But if you assign this region with this pink one, it has no support required at all. So definitely the printing sequence for these black regions will give you different requirement for the printing for the support material. And we consider about this as well. And after the first round of evaluation, we will do a resample near the selected N candidate orientation. Means for the M samples, we just generate the cuboid, evaluate all of these, and then we will sort it according to the support material requirement and find N best one. And around this N best orientation, we will do a resampling and generate another set of samples and generate another set of cuboid and do the evaluation again. We will, yeah, go ahead.
Is there a reason why you do like 45s? You don't have to worry about which order you do them?
What do you mean 45?
So the black areas,
yeah,
you've got the, say the orange
yeah.
piece, it's got vertical wall.
Yeah.
What if you did 45 degrees?
Oh, so yeah.
Is it because of the head collision with the next layer?
So basically, the printing direction will align with the normal of each facet of the cuboid. That means for this region, the printing direction will point in this way. And in this one, we just rotate the base and make this facet point into the upward direction. So
I understand that, but
yeah,
when you print the orange one, you had instead of vertical walls,
yeah,
45-degree walls.
Oh,
and then well, it's 45. So.
Oh, okay. I got your point. But the base is still this base. How could you rotate in 40 degrees freedom?
No, you leave it flat, and then the orange piece that you print that shape, except you also print the 45-degree portion of the black certain area.
Oh, okay. I got your point. Yeah. Yeah. Okay. So you mean this region could be separated into two, and if it's less than 45, you could successfully print it. And okay, that
you don't have to worry about that.
Yeah. Actually, that's a good point. But we didn't at that time we didn't consider about it. That could be a further improvement of algorithms.
You might have issues with your novel.
Yeah. Yeah, that could cause problems, but that's a good direction to think about. But at that time, we just simply either assign this to this region or this region. That is what we did. All right. So we just repeat this process and several times, and turns out there's some result generated like this, and it achieves totally support-free when printing each of the portion. You can just imagine if you rotate that that portion to the this upward, the vertical direction, it does not require support. Right? So the original, the orientation sampling is done by doing sampling on a so-called Gauss sphere. So the Gauss sphere is a uni sphere, and it's centered at the origin. So each point on this sphere could be considered about, you just link the origin and each point on the sphere. And this vector you can consider about as an orientation vector. So that is so basically we map this sampling from the normal vector space to a geometric space. So essentially you just do a sampling on this sphere and find each of the position, and that will be your orientation vector. And that is for the one orientation. And then the two orientation, you can just do it on the uni circle. And because the two orientation in opposite direction, the two vector in opposite direction will give you the same orientation. So you can just do a half hemisphere and a half circle. You just do and saves some computation. Oh. Oh, it starts again. Okay. Yeah.
Paper down there, it says
Yeah.
joint first office. Is that a normal? Is that a normal thing? Joint first office.
Oh, okay. You mean this one, right?
Yeah.
Well, at that time, we basically I propose and develop all the software side, and that guy Wigao, my colleague, he developed all the hardware, and it turns out we kind of think it's equally important for this paper, and both of us need some publication with first author, so we decided to share it. Yeah, that's the situation. Yeah, but actually I think it's normal. Yeah, that is what happened. All right, and we have a filter to.
Publications.
Yeah. Okay, so we develop a filter to kind of exclude the newly generated orientation, which is quite similar to the previous one. So we use this to evaluate how similar the new generated one versus the previous one. If it's too similar, we just exclude it, and that dramatically saves the computation. Only 30% new generated one will be further evaluated. And then we come up with these cuboid generation algorithms. So with one orientation, you could have multiple cuboids inside this 3D object. So how to generate the one with largest volume? So basically, we just start with a very small one, which you can make sure it's inside the object, and then just expand its 6 facets, and expand to a certain level. You can never expand it anymore, and then you will choose the one with the largest volume. Of course, you have to do some collision detection. Make sure what you generated has no collision with the object and entirely inside the object. So we use some trick called the bounding volume hierarchy, and that gives us a dramatic speed up for the search. And that is what we did. Again, we evaluate the oral handling features just using this 45-degree rules, which is quite simple. And the printing sequence, as I mentioned, and there are total 30 different combinations for one cuboid. That is what we came up with. And yeah, let's check the machine. Basically, this is what my colleague developed. It's just a proof of concept one. We use a Ultimaker machine and add a cantilever structure like this with 2 servo motor and air cylinder there. And there are 3-degree freedoms, a translation to fix it and release the cuboid base, and rotate to revolve the cuboid facet, and angular motion to apply gripping force to the handle. So this one is for the handle. In the first round of revolving, there's no use for this handle, but second round, we printed 2 handles, and this gripper will fix it for the second round of printing.
So
yeah.
You said it's an error maker, 930. Have them hand off to each other, so you don't have to have the person get in the middle. Like right now, you kind of had to print a bunch, and then you had to stop and figure out.
Right, there are a lot of there's still a lot of manual efforts here,
Right?
Because we haven't gone that far to fully automate everything. Even the calibration of the system is done by someone. Yeah, because we just we didn't have so much time at that time. Yeah, just prove the concept there.
Picture,
yeah.
Top right picture.
Oh, sure.
Yeah.
Oh, you mean which one you mentioned?
You
mean this one?
That shows a good
Yeah.
kind of balance between edited parts and
Yeah.
purchased parts, right? So you got like, I
Yeah.
see a lot of that stuff probably printed, right? The grippers,
Yeah. Mm.
housing,
Mhm.
fittings and everything.
Yeah, exactly. Yeah.
Patent this concept of multi-axis?
Actually, no. We used to think about to patent it, but we still think it's not that working. There's still some concept, and yeah. So actually, the next version could be some even more automation and degree freedoms. We are thinking about to use 5-axis systems or even a robot manipulator to do this work to further reduce the support material requirement and also automate the whole process. If with the robot's arm, you could do everything automatically if you come up with a good way to do the calibration and also the components placing and so on and so forth. And another good thing is you could have curved layers. Right? Think about if you have, because in this work, we're still using the cuboid. That means it's still planar layers. But if you have more degree freedoms, you could do just an inverse way of subtractive manufacturing, machining, right? Just think about it in that way. Then you will have even better results in terms of the support removal. And maybe there will be some better mechanical property because the layer is not planar. So if you apply some force in certain direction, definitely the strength distribution will be totally different. Actually, that is the direction I'm going towards, and some students, but still a long way to go.
Well, you're making work in a package for your electronics, right? You're
Yeah.
buying these electronics,
Yeah.
putting together.
Yeah.
No, he's saying is you could use it for any, you just have a dumb square.
Yeah.
It's just
Yeah.
an easier way to print
Yeah.
altogether.
Yeah.
So electronics are built on,
The
related
electronics
circuit boards
design.
which are flat. And, there's additive processes where they're coming up with ways to print
Yeah,
circuit boards
but-
in 3 dimensions, right?
Yeah, you could print some wires, conductive wires in 3-dimensional. There's no restriction to be a planar wires because there are already some systems they can print conductive wires in 3-dimensional. So that definitely requires better planning on the wire distribution, how you place your wires. Make sure there won't be some collision between wires. Make sure your printing process will not collide with other parts of the printing. So there are a lot of planning work need to be done there. But restricted by the students and resources, we are slowly going towards that direction. Yeah.
Or it makes
Yeah.
a very similar machine that adds material.
Yeah.
Machine back up.
Yeah.
Uses 5-axis.
Yeah.
What did you print on the POA?
SPLA, yeah. Yeah, SPLA.
Laser
Well, second, it was a higher temperature material. You may overshoot your base plate.
Oh, that's possible.
They've got a slant.
But actually, yeah. But actually, for the multi-axis machine, I could see another potential. You know the cladding, metal cladding printer. Basically, it's just a welding machine, right? It by nature it has multiple degree freedoms. So think about if we come up with some computational method and make this cladding machine to print non-planar layers in multi-degree freedoms, you can really come up with some crazy printing. Not only the shapes, but also a better material property like that. But still, I have no such machine there, so I can only kind of prove my concept using this plastic ones, and hopefully find some collaborator or something. Yeah. And anyway, so this is the result we tested, and you can see we use this support material instead of the conventional ones. Even using this, the comparison is quite encouraging because we achieve totally support free. If if you can see, even for complex shape like this Mark Planck's head and this dog, French bulldog, you can see how complex it is. But if you can find a proper kind of segmentation and orientation, you could achieve totally supportful. So that's the idea. And also we have another functional model generated like this Pokemon, yeah, a Bulbasaur actually. So we just okay. So we just assemble everything like a wind-up motor, a battery in this cuboid, and we put it into this printer and print it. And it turns out we have some fun story like this. Okay, we just take it out and snap off the two handle and insert some LED eyes into these two preset holes, and insert a Pikachu tail to there, and wind it up. Of course, we intentionally to put it above. It's a Pikachu's tail.
I
Anyway.
like the way you pronounce Pikachu.
Oh, really?
Is that like the right way to pronounce it? If we say Pikachu?
You can pronounce anything.
Where's all that from?
Japan,
Man.
Japan, yeah.
Pocket Monsters.
Pikachu on a cartoon.
But that's an English person dubbing over the Japanese. So you pronounce it.
Yeah. Anyway, so
Yeah.
so again, although it's a very simple thing, but you can see the concept. Direct out of 3D printer functionality means what you get from the 3D printer is what you want. There's no, I mean, of course, it still requires a lot of manual work in this proof of concept system, but you can see the concept. We are trying to minimize the manual involvement. We are trying to achieve as much functional component functionality as possible, and we are trying to minimize the support requirement as much as possible. Yeah, that's the concept of this work. Okay, actually we have some time statistic. Oh shoot. Actually, I didn't put the time here, but still requires some 7, 8, or 10 hours because we still use the FDM machine. Yeah, but definitely we will. It requires less time, around 23% reduction on time, around 22% reduction on material. And you may ask, is the reduction is kind of not as much as you guys expected? So what's the problem here? Can you give a guess?
We're still dealing with rectangles, so if you're able to make a shape more complicated than rectangle, you would.
The part you're eliminating is like plaster, honeycomb, right?
Mhm.
They're in the center, that would normally be just the infill.
Yeah, exactly. Because we didn't play with the setup of the original 3D printer much. So it turns out for each of the facets we print, there will be several solid layers over there. If you print in one direction, there will only be 1, 2, or 3 solid layers. But for this one, we kind of have 3 times 6 solid layers. So it cancels out some saving on times and material. So, well, if this project, I mean, if we do it in further stage, definitely that could be a place to work on. And you can see the algorithms it takes, I mean, compared to the printing time is nothing. So, well, that is what we did in the past towards functionality. And I think that is the end of this class, right? And we can have some open discussion. Or something else is also fine.
So is there not rotary tables and whatnot on FDM?
Typically no.
No, looking for project.
Yeah. So actually, at that time, I was seriously think about to keep on working on this, still based on FDM platform. But right now, I'm kind of more think about to try to transfer this technology to the metal cladding-based platform. But again, to prove concept, still on the public basis. But for the application, I think maybe cladding-based will be a better choice.
Try and print on the cylinder.
Then,
Print on the cylinder.
yeah,
And then, so you're constantly overhanging.
yeah, yeah. Actually, that is the immediate direction we came up with for the possible future work. Just to try to come up with complex polygonal shapes instead of just a cuboid. So you will have more direction to play with. And you can see there are a lot of alignment problems. So there will be some gap between each of the parts. That is because the collaboration, calibration is done by people, not that accurate. So you will have such misalignment over there. All right. I think next class we're going to talk about the fuse deposition modeling process and some related technology about that. And yeah, and I think this class will be the end of talking about the design aspects of additive manufacturing.
So
Yeah.
the next kind of deliverable queue is our literature review paper. Is that right?
Not paper, a presentation. And also you need to include them into your final report. I need to see a clear section about the literature review, what you've done in your literature review session, and what are the related work associated with your topics of the project, and why you come up with the idea, why your work is unique compared to the literature, some state-of-the-art work. I think that will be, I always want to help the graduate student to build up the capability to do the literature search, because you have to make sure your research is unique, it's novel, right? And also, before the novelty, you have to make sure your idea is valid. Means you're solving a valid problem, not a fabricated problem or an invalid problem. So these two will be the main target for your literature review. Yeah.
So, I guess I'm trying to figure out
Yeah.
if it's like our project, more of a design project.
Yeah.
We've got things.
You could have a design project or a process project.
Right.
Just as what I gave you posted,
Right.
the two examples. Yeah.
For a design project,
Yeah.
we're going to go through and you do a little review for the values of each of the design
Yeah.
projects, like mechanical properties and issues.
Kind of.
Different kinds of, is that sort of
Yeah,
you would plug in well?
exactly. You have to justify your project first valid, right? And then nobody has done this in this way. I mean, it could be not that much innovation or contribution, but somehow it need to meet the level of the novelty, right? It's kind of a relative stuff. You could talk to me later more and more to make sure what you come up with is good enough for the project. Yeah. Definitely, I would like to discuss with you more about the project. And apparently you all form the team right now, right? Who has no team? Yeah, yeah. And the next next week, I would like to have a group list, who are in which group, something like that, such that I will have. Yeah, I will email you or post a announcement on iLearn to tell you to do this. And also I will post the first homework before the class on this Thursday. That will be your first homework.
Homework will be posted for homework posted before Thursday.
Yeah, for Thursday, and I will give you 1 to 2 weeks. It depends on. I think 1 week should be fine. Okay, 2 weeks. Fine. We won't have too much homework. I want to make it a project centered course. The homework is just to kind of remind you what are the points you need to pay attention to. So it's all about the project. That will be, I think for you guys, you don't need to do too much those kind of homework or writing, but more focus on the project. That will benefit you for your future study, a graduate study or research. All right? Okay. Yeah. Okay, good. Yeah.
5 axis FDM.